Hello, everyone. Welcome to the Interview Hub. If you're preparing for a PySpark interview, you're in the right place. In today's video, we'll discuss the most frequently asked PySpark interview questions, along with clear and concise answers. Before we get started, if you haven't watched our previous video on the top 5 most frequently asked PySpark interview questions, be sure to check it out. It will help strengthen your PySpark fundamentals and improve your interview preparation. Now, let's get started. What is the Catalyst Optimizer? Answer. The Catalyst Optimizer is Spark SQL's query planning engine. When you write a data frame operation or SQL query, it doesn't run immediately. Catalyst first converts it into a tree-based logical plan, then runs it through several transformation phases to produce the most efficient physical execution plan before any code actually runs on the cluster. 1. The input unoptimized logical plan. The funnel. Your raw query, like a SQL statement or data frame operation, enters here as a messy tree structure. At this point, Spark doesn't know if your column names actually exist or what data types they are. Stage 1, analysis. The blueprint check. The query enters the analysis chamber, represented by the gears. The fix? Spark looks up its internal catalog to match your table and column names, fixes data types, say converting text numbers to integers, and outputs an analyzed logical plan. Stage 2, logical optimization. Rule-based optimization, RBO. The plan enters a machine that repeatedly applies logical rules. Shortcuts like push-down filter happen here. For example, if you only want data where age greater than 21, Spark moves that filter as close to the data source as possible so it doesn't read unnecessary data. The loop. The pipeline shows a loop called recursive applications of rules. The plan spins through this loop until no more rules can make it any simpler, resulting in an optimized logical plan. Stage 3, physical planning. Cost-based optimization, CBO. The optimizer calculates different physical plans, the literal computing strategies to get the data. It uses a cost model, the calculator icon, to look at statistics like data size and network costs. Strategy selection. It chooses the most efficient mechanism for data partitioning, join types, like choosing a hash join versus a sort merge join, and scan methods, based on what will execute the fastest on the cluster. Stage 4, code generation, whole stage code gen. The JVM chip. Instead of running the steps one by one like a slow recipe, Spark passes the final physical plan onto a compiler. The output. It flattens the entire process into highly optimized Java bytecode, optimized executable bytes, that runs directly on the Java virtual machine, JVM, at bare metal speed. The output physical plan. The final executable tree. Out comes a highly optimized concrete blueprint ready to be split across the cluster machines and executed immediately. The result feeds into RDD execution across the cluster. This is why writing df.filter.select.groupby in a less efficient order often performs identically to writing it in a more efficient order. Catalyst rewrites the plan either way, something you don't get with raw RDD code. What is directed acyclic graph? Answer. In Apache Spark, a DAG, directed acyclic graph, is the brain behind how your data processing code gets transformed into a highly optimized execution plan. When you write Spark code, like filtering rows, grouping data, or joining tables, Spark doesn't actually run those operations immediately. Instead, it records them as a sequence of steps. That sequence of steps is the DAG. How Spark builds and uses a DAG. The lifecycle of a Spark DAG relies on 2 main types of operations, transformations and actions. 1. Lazy evaluation, building the graph. When you call a transformation, like .filter or .map, Spark doesn't touch the data. It just adds a new node to the DAG. The nodes represent the RDDs, resilient distributed datasets, or data frames at various states. The directed edges, arrows, represent the operation transforming the data from one state to the next. Because it's a DAG, the flow is strictly one way, and it's impossible to create an infinite loop of transformations. 2. The trigger, executing the graph. The DAG remains a blueprint until you call an action, like .count, .collect, or .save. The moment an action is called, Spark hands the DAG over to the DAG scheduler. The scheduler looks at the whole graph, optimizes it, like combining operations to avoid scanning data twice, and breaks it down into a hierarchy of stages and tasks to distribute across your cluster. Narrow versus wide dependencies, how Spark splits the DAG. When the DAG scheduler looks at your graph, its main job is to figure out where it needs to shuffle data across the network. It splits the DAG into stages based on how data depends on the previous step. Let's understand narrow dependency versus wide dependency in PySpark. In a narrow dependency, each parent partition is used by only one child partition. Operations like map and filter follow this pattern. Since data doesn't need to move across machines, Spark pipelines these transformations within the same stage, making execution faster and more efficient. In a wide dependency, multiple child partitions depend on data from the same parent partition. Operations such as group by key and join require a shuffle, where data is transferred across the cluster. Because of this, Spark creates a new stage, which increases execution time. Remember this interview tip. Narrow dependency means no shuffle and better performance. Wide dependency means shuffle, a new stage, and higher execution cost.
A concrete example. Imagine you have a log file of e-commerce website traffic, and you want to count purchases by country. Python. 1. Read data. Transformation. Node A created. Logs equals spark.read.json, hdfs/logs/star. 2. Filter for purchase events. Transformation. Node B created, narrow dependency. Purchases equals logs.filter, logs.action equals purchase. 3. Group by country and count. Transformation, node C created, wide dependency. Counts equals purchases.groupby country.count. 4. Trigger execution. Action, counts.show. Here is exactly how Spark handles this DAG. Stage 1. In-memory pipelines. Spark reads the data, node A, and filters it, node B, simultaneously on individual worker nodes. Because filtering is a narrow dependency, no data is exchanged between servers yet. The shuffle boundary. To group by country, node C, Spark hits a wide dependency. It writes the filtered data to disk and shuffles it across the network so that all USA logs end up on worker 1, all India logs on worker 2, etc. Stage 2. Final aggregation. The worker nodes count the shuffled data and output the final result to your screen. Why is the DAG such a big deal for Spark? Fault tolerance. If a worker node crashes mid-calculation, Spark doesn't have to restart the whole job from scratch. It looks at the DAG, figures out exactly which partition of data was lost, and recomputes just that specific piece from the original source. Optimization. By looking at the whole graph before running it, Spark's Catalyst Optimizer can rearrange operations, like pushing filters closer to the data source so it reads less data off the disk from the very start. What is lazy evaluation? In PySpark, lazy evaluation is a core design philosophy where Spark doesn't execute data transformations immediately when you write them. Instead, it waits until you explicitly ask for a result. Rather than running each line of code step by step, PySpark treats your transformations as a recipe or an execution plan. It only cooks the meal when you actually sit down to eat by calling an action. Here is a breakdown of how this works using PySpark concepts. 1. The 2 types of operations in PySpark. To understand lazy evaluation, you have to look at how PySpark categorizes its operations. Transformations, lazy. These operations define what you want to do to the data, but they do not actually compute anything. They just build your DAG, directed acyclic graph, blueprint. Examples: .filter, .select, .map, .groupby, .join. Actions, eager. These operations are the triggers. They tell PySpark, okay, I actually need the output now. An action forces Spark to look at the entire DAG blueprint, optimize it, and execute it across the cluster. Examples: .show, .collect, .count, .first, .write.csv. 2. A real-world analogy, ordering at a restaurant. Imagine you go to a fast food restaurant. You tell the cashier, I want a burger, transformation 1. You add, make it no onions, transformation 2. You add, and give me a side of fries, transformation 3. If the kitchen was not lazy, they would have started cooking a standard burger the second you said burger, then thrown it away when you said no onions, and then started cooking fries. That is incredibly wasteful. Instead, the restaurant uses lazy evaluation. The cashier writes down your entire order on a receipt, building the logical plan, or DAG. Nothing is cooked yet. Only when you pay and submit the order, the action, does the kitchen look at the entire receipt, optimize the process, cooking the burger without onions from the start, and hand you your food.
3. Why does PySpark do this? The benefits. Lazy evaluation isn't just about waiting. It allows PySpark to make highly intelligent decisions under the hood. A. Query optimization, the catalyst optimizer. Because Spark knows your entire plan before it starts processing any data, it can optimize the execution path. Filter pushdown. If you load a massive dataset of 1 billion rows, perform 5 transformations, and then filter for country equals Canada, Spark's optimizer will rewrite the plan to apply the filter right at the beginning when reading the data. Instead of loading 1 billion rows, it might only load 10 million, saving massive amounts of memory and network speed. B. Fault tolerance. Because Spark keeps a record of the entire recipe, the DAG, it is incredibly resilient. If one of your worker nodes crashes mid-calculation, Spark doesn't have to restart the whole job. It simply looks at the recipe, identifies exactly which piece of data was lost, and recalculates just that specific part from the source. Summary. Transformations build the recipe, DAG, but do nothing to the data. Actions trigger the execution of the entire recipe. This delay allows Spark to optimize performance and handle failures gracefully across massive clusters. What is broadcast join? A broadcast join is a way PySpark speeds up joins between a large data frame and a small one by avoiding an expensive shuffle. The problem it solves. Normally, when you join 2 data frames, Spark needs rows with matching keys to end up on the same executor. If both data frames are large, Spark shuffles both of them across the network, so matching keys land together. This is a shuffle join, sort merge join, and it's expensive. How a broadcast join works instead. If one data frame is small enough to fit comfortably in memory, Spark broadcasts, a full copy of it to every executor. Then each executor can join its local partition of the large data frame against the small one entirely in memory. No shuffle of the large dataset needed at all. When it happens, Spark does this automatically if the small data frame size is under a threshold, controlled by Python. Spark.conf.get, spark.sql.auto-broadcast-join threshold. Default 10 megabytes. You can also force it explicitly. Python. From pyspark.sql.functions, import broadcast. Result equals large_df.join, broadcast small df, on ID, how inner. Why it's faster. Skips the shuffle stage entirely for the large data frame. Each executor does an in-memory hash join, which is much cheaper than a sort merge join across a network shuffle, over a network shuffle. Thanks for watching. Keep learning. Like the video, comment your questions, subscribe to Interview Hub.